Okay, so hello, I'm presenting my little project I've been working on. It's a Vulkan 3D and 2D renderer. So I guess I'll start by showing what has been made. So here we can see a 3D scene. The car can drift, can turn. The faster we go, the slower it turns. We have some cameras moving, probably notice. We have ability to look around a tiny bit. Some basic lighting, the blind fong with a directional light. You can see here on the car. That has not advanced very far because that's not been the main focus of the project. The main focus has been this, which is the 2D render. This is a 2D renderer that is drawn, everything here is drawn in a single draw call, like on a big triangle. It's based on a talk given at DevCam. It's a talk on UI Painter by Guerrilla Games. I'll link it in the description. This is basically the implementation of what the talk was talking about, or at least my understanding of the described idea. As we can see here, we have some simple UI. Like we have some buttons, some kind of containers. This is a container that lays out stuff horizontally. The main thread, like the main window, lays it out vertically. You have some buttons which print something. It can also interact with the game, right? You have a car goes this fast. You can increase the car speed, and now it goes a lot faster. Right? You can make it turn a bit faster, and then it'll kind of spin. So yeah, this can be used as for tooling. That's how it looks. We have also an input text box, of course, which we can type into. It can also take the text out of it. We have, for example, a color picker, which is now the glow outside of these boxes is white, but how it is red, we can set it to red, blue, any kind of different shape, color, shade. We have also check boxes. Many others could be implemented very, very easily. Now, how is this everything here is drawn? Everything here is drawn at single draw call, and then these primitives are drawn using the shader. So how this works is we have a draw command struct, which you can find over here. Here's how the struct looked like. This struct basically tells the renderer what to draw, where is it on screen, and some other stuff. Like the renderer supports rectangles, which, for example, the backgrounds of these buttons, outline the rectangles, basically every outline here, this as well. Text, which is basically a rectangle that samples a text texture, the font texture. It as well samples just normal textures, but we don't have any other texture currently than the text texture. There could be different ones. Gradient rectangles, like this one here, linearly interpolated colors. This is not a texture, this is computed on the fly. Glow stuff, what's the color of the glows? Yeah. All these are just sent to the GPU as a single array. Next, what the GPU does is every pixel tests how far is it primitive, since it's based on signed distance fields. So it mathematically computes, did it draw the color of the outline or maybe the color of the background? It does that for every command. However, that would be terribly slow if we went and did that with just naively making it. That means that every pixel tests every single draw command. Like even in this simple UI, you already have few hundred draw commands, which just makes the GPU suffer because every pixel does the same 300 tests, even though, for example, most of these pixels over here don't need to test it. They probably don't need to do anything apart from like one test against the background. So what we introduce is a tile renderer, which here is an overlay showing that. What the tile renderer does is it splits, kind of pre-computes some of the stuff. We can see the tiles, which is the kind of rectangles here. These are pre-computed before uploading the tile information along the draw commands to the GPU. What these allow the shader to do is to kind of check which draw commands it should check. Right? So for example, the pixels in this kind of rectangle where would check only, let's say, this outline, this background, and this outline here, nothing more, and this the background of the whole UI. But it will not check any of these. And we do that in like on a CPU as a pre-processing step. We pre-generate this tile information. So yeah, these tiles are 32 by 32 pixels, which has been outlined in the talk that I mentioned. This is because on most GPUs, this is how big it fits nicely with how the compute units are allocated on the GPU actually. Like for example, on NVIDIA, the warps, they're allocated. So yeah, that's the UI basically. What I'll show next is basic project structure, how stuff is laid out here. It is laid out pretty similarly to how a handmade hero is. So here is the actual game, which draws the UI, just as I mentioned, immediate mode. So if we draw a button, we also can check if the button is pressed at the same spot, so we don't have any issues with like invalid data being shown, because if we render the UI, we also update it at the same time in the same place in the code, which makes it simpler to build UIs quickly and make them useful. Also, the UI building is very, very fast, so that also is nice. We can do it every frame. But yeah, generally, the architecture is split into 3 different things, which is the game, which is here, and the platform layer, which the game sits on top of. And the platform layer expects 2 functions from the game, which is this, for example, game update and render, and the game init. The platform layer calls these functions at certain points in time. Game init is called when we initially start the game, and then game update and render is called upon every frame. I'll now move on to the platform layer. Give me a moment. Here we go. So in the platform layer, you can see this file basically describes everything that the game is going to touch from the platform side, plus some helpers that are shared between platform and game, like the types, the math stuff, some basic macros for linked lists, dynamic arrays based on Sean Barrett's dynamic array implementation. Also, we'll link that below. Strings, parsing, arenas, which is a linear memory allocator. It allows me to simplify the memory management, because I group allocations together, and then if I'm done with something that was generating a lot of these allocations, I just clear the whole arena and I'm done. It also allows me to do temporary allocations, scratch space, which allows for the formatting of certain stuff. Like for example here, you can see that this is formatted every frame, and it's the string that is shown here is allocated on this scratch arena. This arena is reset every frame, so we never overflow, like we are not leaking memory. Since allocations are very fast and frees are very fast on the arenas, we can allocate in a lot of stuff and a lot of stuff as well. And it's not an issue because we reuse the same memory over and over. There's some other stuff, some inputs. It's how controllers are tackled. Keyboard input, mouse input. Here are things that the platform layer calls. Here are, for example, stuff that the game calls, like virtual memory operations, page size, which is platform dependent, debug break, which just calls int3 or raises the sig break. Also, like key and mouse input, as well as loading files. That's what the arena is. And now the third component of the input structure is the renderer, which exposes a few things. These are to the platform. This platform initializes the renderer. We call the renderer begin and end frame. That's the renderer we want to start and stop the finish frame rendering. Some matrix operations, some tile mask. For example, this tile mask enable is literally this toggle here. This is what the toggle goes to. The 2D drawing operations, and now here the 3D API is different than normally, because we don't explicitly load meshes and assets. What is happening, we create a key, which in the game, it's easier to maybe visualize. We have the keys here. We update the key from a string. The string, in my case, is a path. Since currently the asset is on the file system, for example, if we would ship the game, we probably would we would embed it into the binary or store it in a bit more complex way than just bare asset files that are exported from Blender. We just get the asset path, but we don't load anything here yet. Then when we call the draw, here, we're drawing the car, we just draw a model. And then the renderer takes care of loading the model, making sure there's enough space for the model, and rendering it. I'm doing it this way because then, for example, if we would switch scenes and we would load a lot more new assets and we would need to unload some assets, because, for example, we are on a lower end platform, something on a console, we don't need to, from the game code, we don't need to unload anything. We don't need to worry about that. The unloading is done by the renderer. As the renderer runs out of memory, for example, for the models, it starts kicking off from the cache, the loaded model. And that's basically how my project is. This is my little tiny toy project. 3D and 2D renderer, written fully in Vulkan. In 3,000 lines of Vulkan, plus some helpers. Thank you very much.